You have the list of amino acids, and as I said, there were some questions people asked how much do you need to know about the structure of the amino acid. You should know enough so that if you are given a structure, you should be able to tell this is the amino acid. Alright, so that's one way of understanding that if you are given a structure, you should know this is the amino acid. You should know which are the amino acids that are hydrophobic, or which are the basic amino acids which have an extra amino group or extra carboxyl group. So you remember it that way. You don't have to know exactly how many carbons. You just need to know that the glutamate has a group of carbons, right? If you know the formula of glutaric acid, you should be able to do that because it is derived from glutaric acid. If you don't know, but it's okay, just a couple of amino acids, a couple of carbons away is the carboxyl group. So of all the amino acids that we have looked at, the smallest one is of course glycine, and there is only one amino acid that is not chiral. Which one is not chiral? This is the type of information you should know from the structures. So it is glycine, right? That's the only amino acid that is not chiral. All other amino acids have 4 different groups on the carbon. And so glycine is the smallest amino acid, and in some cases it is actually too small. So the next smallest amino acid is alanine. Instead of a hydrogen, it has a metal group. You should know which are the ones that have hydroxyl group, like serine has a hydroxyl group, tyrosine, threonine. And aromatic ones, phenylalanine, tyrosine, tryptophan, they have the aromatic ring. If you look in the list of pK values, I gave you a list of pK values, it's in the book also. So all the amino acids are alpha amino acids, as I wrote last time. That means the carboxyl group and the amino group are on the same carbon. So this is the carboxyl group, this is the alpha carbon, and if you have more carbons here, that will be the beta carbon, gamma carbon, like that. So for glycine, this is a hydrogen. So in this, the correct way of writing this is to have, I explained that last class, that the handout that I gave you has the side chain shown here. And if you want to put the side chain at the bottom, then you need to switch 2 groups, because that's what you learned in organic chemistry. If you switch 2 groups, it becomes the same molecule again. And so if you want to have the side chain at the bottom, then you need to switch these 2 also, so the carboxyl group should be written on top. Then it will be the same stereochemistry. The stereochemistry, in organic chemistry, you learned about R and S structures, which is not used much in biochemistry. Most of the time we talk about Fischer projection. And Fischer projection, organic chemists don't like at all. Why don't they like the Fischer projection? What's wrong with the Fischer projection? The Fischer projection is always drawn in the eclipsed conformation. If you have 2 chiral centers, you have to make it the eclipsed conformation, and then you draw the Fischer projection. So that means the actual structure of the molecule doesn't resemble the Fischer projection as shown, but biologists love it, pharmacists, medicine people, everyone loves the Fischer projection, except the organic chemists, who always use the R and S. So the problem with Fischer projection is you have to have rules about how to draw each class of compounds. which one you put the horizontal line, which one you put on the vertical line. There has to be rules about that. For example, in carbohydrates, as we will study later, you have to draw the carbohydrate with the aldehyde group on top and the rest of the atoms at the bottom of the chain. In the same way, you have to have a rule for every class of compound. For the amino acids, the rule is the nitrogen is always written on the left side like this, and if it is on the left side, it is L amino acid. If it is on the right side, it is D amino acid. And all natural amino acids are L amino acids, so we won't see it written any other way because amino acids are always L amino acids. Whereas carbohydrates, they are all D carbohydrates. And so it has to be written in that way. Now remember, whatever is on the right side will be on the left side if you write it the other way. If I put this one down, it becomes opposite as putting it up. So that's why for Fisher projection it is so important that you follow a rule about how to draw the structure. Then only if the amino group is on the left, it is L. And one good thing about natural things is that they all have the L amino acids. So that's why we have all the amino acids with the amino group on the left side. All right, so the pKa, as I mentioned, there are two pKa's, and the pKa of this one, the carboxyl group, is around 2 point something, and the pKa of the amino group is around 9 something. And once again, people always talk about pK of the amino group. It is not really the pK of the amino group, it is the pK of the ammonium group. That means the NH3+. So if there is a third group somewhere here, let's say there is a carboxyl group or a amino group that will have another pK values. And usually if it is a carboxyl group, the pK will be between 2 and 4.8, which we saw last class. 4.8 is the pK of any carboxylic acid, like acetic acid. So this will have a pK around less than 4.8, but it will be more than 2. Why is that? Why is this 2 and not 4.8? Acetic acid has a pK of 4.8. This one is less because of the positive charge of the nitrogen, which withdraws electron from this hydrogen and makes it ionize better, and that makes it a stronger acid. So that's called the inductive effect of the amino group or ammonium group, makes that a stronger acid than carboxylic acid, so it has a pK much lower than 4.8. If there are several carbons here, let's say 3 carbons as in glutamate, this carboxylic acid will be a stronger acid than acetic acid. But that's not really predictable because what factors decide how easily this will ionize? It will be the inductive effect of the NH3+, which will withdraw electron from the COOH bond. Let me write the. So this nitrogen withdraws electron from here through these bonds, and that inductive effect makes this a stronger acid than acetic acid, but this distance is much larger than here, and so the effect is not as much. However, there is another opposite effect, that is the effect of the negative charge. So this negative charge will have an inductive effect as well. That will make it a weaker acid, not a stronger acid. So it is the net result of these two that make this pKa somewhat close to 4.8. It is not too much lower than 4.8 because you have two opposite effects happening from the carboxyl group and the amino group. So both have an effect on the pKa, and the net result can only be decided by looking at the number in the book. One of the amino acid is an interesting one, you need to know that, and that is histidine. Histidine is the only amino acid that has a pK of the side chain at around neutral pH. It has a pK around 6 or 6 point something. That is the closest to the neutral pH of the water or of the cell. And that becomes important because if the pK is in the neutral range, then it can very easily gain a proton or lose a proton. What does the pK decide? If your pH is lower than the pK, then it will be protonated. What does protonated mean? It's not ionized. If the pH is higher than the pK, then it ionizes. So at neutral pH, histidine is the only one that can both gain a proton and lose a proton depending on the local environment of that. So even though water is the main solvent in the cell, the local environment of every amino acid is different in the protein. So whatever pK values are given in the table of the free amino acid, that really has not that much meaning because in a protein, those pKs are all different. Because in a protein, you have not just one amino acid, but you have many amino acids like this. And a carboxyl group here will have an effect on an extra amino group here, somewhere far away. Remember, it may look far away, but in a three-dimensional structure, the amino acids may be close to each other. So this is not the structure of the protein. The structure of the protein is something like this. And this COH may be close to this amino group, and they have a strong effect on each other in their pK values. So all the pK values of the side chains given in the book or in any table for any of these amino acids are only valid for the free amino acid, not in a protein. In a protein, they may be different. So even though they are different, it will be in that range, and histidine is the only one that can fit in the range of the neutral pH. And so histidine is at the active site of many proteins. It decides whether it will be accepting a proton or releasing a proton. There are many reactions that happen. They are acid-base reactions. Something gains a proton or something loses a proton, and all those reactions, the proton must come from some amino acid at the active site, and that most likely amino acid is a histidine, because that's the one that can both gain or lose a proton depending on the local environment of the protein. So in many cases you will find that histidine is an important amino acid in a protein. Let's look at any of these amino acids and decide what will be the species present as you increase the pH. So you can start with any amino acid, doesn't matter which one. So I'm not writing the R group, it can be any of these. So if you are below pH 2, so let's say the pK of this one is 9 and this is 2. They are not exactly that, but depending on the amino acid. So if you are below pK 1, so this is pK 1, and this one is pK 2. It's also written as pK 1 or pK 2 without the A. So if you are below 2.0, so if this is 2.0 pK, I'm just making up these numbers, and this is 9.0. So if you are less than, so if the pH is less than 2.0, that means you are lower than the pK of this one and lower than the pK of this one. So what will be the species at lower than pK? It will add a proton to it. That means it will be deprotonated. So this will have a proton, and this will also have the proton. It will not ionize. So this is the species at pH less than 2.0. As you increase, you add sodium hydroxide. You are increasing the pH. When you go above 2.0, then this will start to ionize. So the species then will be NH3 plus. So below pKa2 it is protonated, above the first pKa it is deprotonated. And then as you keep adding more sodium hydroxide, when you reach the pH above 9, then this will also be deprotonated. So now this will become NH2 . So what is the charge on this one? The total charge is +1. The total charge of this one is 0. There is a plus and a minus. And the total charge of this one is -1. So the pH at which it has a 0 charge, if you put an electrode in the solution, then the species will not move towards the negative or positive electrode. If you are doing it at a lower pH, then this will move towards the negative electrode, this species moves towards the positive electrode, this one doesn't move in either direction because it is equally charged. So any species that has 0 net charge is called a Zwitter ion. So Zwitter ion means all the molecules have a 0 charge. And so it doesn't move towards either electrode. And the pH at which that happens is called the PI for isoelectric point. So isoelectric point is the pH at which all molecules will have equal number of plus and minus charges, and so it doesn't move in either direction in an electrical field. So this is a characteristic of amino acids, just like melting point, boiling point, these are characteristic of any molecule. So PI is a characteristic of any amino acid. So you can have a table of PI values somewhere in the book if you look for it. And once again, the PI values are only meant for the pure amino acid. It's not meant for that amino acid in a protein environment, because in a protein environment, it's totally different environment, because the amino acids are not next to each other. Yes?
Do atoms have an impact on the charge?
No, because pK is already decided by the atoms. So pK is the net result of every factor, and the pK is known or given to you in the book. So at a certain pH, then this will be isoelectric point. So what will be that pH? If this is 2 and this is 9, when will this be equal amount of plus and minus? It will be right in the middle of the two, right? So the PI you can actually calculate will be equal to the average of pK1 plus pK2. So that's how you calculate the PI of an amino acid, is the midpoint of pK1 and pK2. Yes?
I just wanted to ask a point earlier. You said when the pH is less than 2, is it protonation or deprotonation both?
It's protonation. Lower than pK means you are adding a proton. It is not ionizing. Higher than pK, it ionizes. Same way for the amino group. If you are lower than the pK of this ammonium group, which is 9, so 2 is obviously lower than 9, so it will remain protonated. That means it will remain as NH3+. It will lose that proton only when you go above 9. Yes?
So if we have like a PK3, that would affect the PI calculation.
PK3 and even another one, the third one. So let's do a third one. That means you have three pK values, right? have a third carboxyl group, and the pK designation is that this is called pK3. So what these are, the alpha ones are always 1 and 2. Even if you have an extra amino group, that will be the pK3. Extra carboxyl group, that is the pK3. So for this one, as I mentioned, this will have a pKa higher than 2.0. So let's just pick a number. Let's say it is 4. All right. So the pKs are 2, 4, and 9. So as you add sodium hydroxide, so this will be below 2.0. This will be the species. This will be protonated. This will be protonated, and this will also be protonated. As you increase the pH, when you go above 4, then above 2, this one will ionize the alpha carbon, that pK1, and this one will not. So that means between pH 2.2 to 4, 2.0 to 4, this will be the species. Yes?
Professor, you said it's going to increase what?
Correcting what?
You said it's going to increase what?
You are increasing the sodium hydroxide. So you are increasing the pH. So as the pH goes from less than 2 to more than 2, but not more than 4, then this will ionize, but not this one. As you go to pH more than 4, so if you go above the pK3, then this will ionize. So between 4 to 9. Alright, so when you go above 9, then this will also lose the proton. Alright? Yes?
Is the PK2 always going to be that R3?
No, by definition 2 is alpha alpha amino group. So this is 2, this is 1, this is 3. So the side chain is always 3.
Like, would you ever ask us to identify which one is which? Or
I don't know what I will ask. But that's what I said. The alpha pK is always the lowest. Yes. No, this is 3. This is the acidic amino acid. 3. For basic amino acid also 3. There is no amino acid that has 4. Alright, so at what point is it which one is the Zwitter ion? The Zwitter ion is this one. Right, 1 plus and 1 minus. And at what pH will that happen? It will happen between this and 4.0, because if it goes above 4.0, then it starts to have an extra negative charge. So for this one, then Pi will be the average of pK1 plus pK3. Alright, so if you can do the same type of exercise with the extra amino group, this is the general rule you will come up with, that the Pi is the average of the carboxyl group and amino group if there are only 2 of them. That means there is no extra carboxyl group. If you have an extra carboxyl group, that means it is acidic, then it is the average of the 2 carboxyl groups, this pK and this pK. If you have 2 amino groups, then it is the average of the 2 amino groups. That is the Pi. So if you take an amino acid that has a extra amino group with a pK of, let's say, 12, then the Pi will be average of 9 and 12. Alright, so very simple rule. If you have two carboxyl group, the pi is midpoint between the two carboxyl pKs. If you have two amino groups, it is the average of the two amino keys. If you have one of each, then it is the average of the amino and the carboxyl, which is true for most of the amino acids. Some of them not, some of them have carboxyl group, and that will decide the pi. And once again, these pi values are for the pure amino acid. It just gives you an idea of what the actual pi will be for that amino acid in a protein. All right, so when we did the phosphoric acid or the carbonic acid, so the titration graph looks like having two flat regions, and same thing will happen with the amino acids because they have two pK values, just like having two acids. So it will still look like the same. So if you plot pH versus equivalence of base, so it will start like this, become flat, pH. Same way for a diprotic acid. Yes. Yes. When do you want it?
7 years.
How about in 2 weeks? Remember one thing, the quiz is only 5% of the total grade. So the purpose of the quiz is not really to give you that 5 points, how much, whether you get 4 out of 5 or 3.5 out of 5 or 1 out of 5. And the purpose of the quiz is to give you a sample of what the questions will be like. Yes. Yes.
Are your quizzes and tests like multiple choice and short response?
Yeah, they're all multiple choice. So the purpose of the quiz will be to give you samples of actual what do you say? No. That's why you need to come to class. Whatever we're doing there, that can be the Yes, well, all questions will be from what we do in class and nothing from outside. Yes.
You said that you also refer to the textbook. Can you tell us what questions to look at in the textbook?
I haven't myself looked at it. People ask what book to follow. This is basic biochemistry. If you don't want to spend the money, you get a cheap book from somewhere, that is fine. This information will be there in any biology.
I don't spend money on books, I don't know.
But what? Oh, the questions, I think so. I don't know much about the questions, how many hours,
In all seriousness, Professor, I do understand that the exams are 85% of our grade.
Right.
You're giving us only notes based on the board, and some of us we can't read them. And I don't think the notes are just enough for us to be
That's why you
examined.
have the book.
But you're not giving us clear instructions with the
What
book.
kind of instruction you want? These
What
are
questions we should focus on.
not questions, what topics?
Or even topics. You're not being clear, Professor. This class,
Yeah.
the exams are worth 85%. We don't
Right.
have the opportunity to fail an exam. We need clear instructions on what we should follow.
This is what you follow. Whatever topics we are doing in the class, if you want to get it from a book, that topic will be in the book. If you pick any book, biochemistry book, it will have that topic. And if there is some information in it that we haven't done in class, you are not responsible.
It's this great. It's actually this great. Like, this is like the smartest person I know.
Say that we need at least slides that say what we're taking what's the highlights of the exam, what we have to focus on, some practice questions, some, study guides.
The quizzes will give you sample questions about what kind of questions. So as I said, whatever we do in class, that is what you're responsible for. The moment I give out slides, the attendance in the class will become down to 20%. Because people have the false impression that you have the slides, so you don't need to come to class. You don't need to come. Because you have the
I promise that give me slides and I was.
I don't have slides, I'm writing on the board, I don't have any.
I will come no matter what. I promise I will come no matter what. I just want to slide the guy down.
Have these professors can be like, oh yeah, I
All right,
some cards.
yes.
Professor, I don't mean to be disrespectful in any regard. I'm just really concerned about our future grades because we are in T3 and one failure, one F in one class will get us kicked out from the program. So I'm coming from a place of deep concern. Can we please, I understand you want every one of us to come into class. I know it wasn't fair for you to get assigned to teach this class last minute. I understand, but you have to understand that we're still paying out of pocket. We're still paying our tuition. I feel like the least you could do is at least record. If you don't want to give us notes, okay.
There are at least 20, 30 people recording.
Yeah, but they're
the
not
lecture.
sharing it with the rest of the class.
You record your own. Why can you not record your own?
I don't have the phone storage.
People take notes. They don't have to share it with you.
Genuinely good.
They take their own notes.
No, I know. Well, listen, we got the only time I pass this out
Alright. So the graph. So the graph is basically the same as the diprotic acid that we did. So there are two pKs, so there will be two pKs where it will become like a buffer. So it increases, and then at this pK, which is the, let's say 2.0, the first pK, and at the second pK, pK2, it will again be straight line like that. If there are 3 pKs, then you will have three graphs of this kind. pK1 and 2, because this has 2 pKs. If there are 3 pKs, then you will have a graph with 3. So it will look like this, like this, and like this. So pK1, pK2.
The top one or the the bumps are just the like the way
We did this in the weak acid chapter 2. When you titrate a weak acid with the base, this is the type of graph that it looks like. The pH increases, and then it remains constant, then it increases, then it remains constant. Where it remains a constant, that's where it acts as a buffer. And we did the calculations there, like between plus minus, between 10% to 90% neutralized, it will more or less remain constant, plus minus 1. So refer to your notes on the weak acids, how the graph looks like, and the amino acid will look exactly the same. No, it's not in the chapter. It's chapter 3. We are not doing chapter 4, which is on purification of proteins. That's from page 5. This is chapter
What you just wrote on the board, that's for amino acid data citation.
No, the second one I do was
This is how I Is it bad? No, I'm good. You just have to focus. Also,
and the first one I do was with all right, so this is the amino acid depending on the R group. This can combine with another amino acid. So let's say this is R1 and R2, and you can remove a molecule of water from these. Let me write the arginine here. And if you remove a molecule of water, you form a bond between the carboxyl group and the amino group. So this CO combined forms a bond with this NH. So you have formed a bond between the two amino acids by removing a molecule of water, and this linkage from organic chemistry, you know this is an amide bond, which in biochemistry is called a peptide bond. So peptide bond is the CONH bond. It's called the peptide bond between the two amino acids, and because it is between two amino acids, this is called a dipeptide. In the same way, this can combine with another amino acid on the left or on the right, and thus you can keep adding more and more amino acids. So if you have 3 amino acids, that will be a tripeptide, and that way if you have many, that will be a polypeptide, which is also called a protein. So a protein consists of amino acids linked this way, one after another, and it is always the alpha carboxyl group and the alpha amino group that participate in the peptide bond formation. So the side chains don't. So these side chains, if they have a carboxyl group, that stays, or a amino group, that also stays.
What about alpha groups? Alpha groups and
Whatever group is in the side chain that doesn't form a peptide bond. It is the alpha carboxyl and amino group that forms the peptide bond. So this way then, instead of drawing the whole structure, let's say you have amino acid 1 linked to amino acid 2 linked to amino acid 3. So this way you will have many amino acids forming a protein, usually more than 100. Most of the proteins will have more than 100 amino acids in the chain. And as I mentioned in the first class, proteins have a fixed sequence. So based on the R group, this amino acid has a name, this amino acid has a different name, this amino acid. So this way, one after another, the amino acids will be joined, and the order in which those amino acids are joined is called the sequence of the protein. And a protein is defined by that sequence. It cannot be a different sequence. It cannot be at random joining of amino acids. It has to be in that order. If it is not in that order, then the protein will not have any activity. So for all proteins then, if you keep adding like this, the first amino acid will have a amino group that is not linked to anything else, and the last amino acid will have a carboxyl group that is not linked to any other amino acid. So this way then a protein has a direction, and it is called the N terminus and the C terminus. So all proteins have an N terminus and a C terminus. Now molecules really don't have any left or right, they just keep on moving in all directions. But for the purpose of a convention, so that everyone understands the same thing, people have decided that when you speak of a protein, you should always read the sequence or tell the sequence starting from the amino terminus to the carboxy terminus. So if you are asked what is the sequence of this protein, you have to start from this end. This may be a alanine, this may be a tryptophan, this may be a tyrosine. So you read in this direction from the amino to the carboxy terminus. There is no specific scientific reason for that. Only reason is that you want to follow the same convention for everyone. So if you take all the amino acids and look at, they are of course all different sizes, but you can always take an average of all the amino acid molecular weight, and that molecular weight comes to 128. And because you have hundreds of amino acids in a protein, you can more or less get an accurate picture of the size of the total protein if you know how many amino acids. It may not be exact, but if you take if you are told there are 100 amino acids, you multiply by the molecular weight, and that should give you more or less the molecular weight of the protein. But when you do that, you don't really multiply the 128 by the number of amino acids. You actually multiply 110 by the number of amino acids. This gives you the molecular weight of an estimate of the molecular weight of the protein. Why is it 110 and not 128? Yes. The average of the atomic molecular weight of all the amino acids is actually 128, but you use 110. Why?
Yeah, the extra H2O bonds in the middle that
because you are losing a water for every peptide bond, right? So that you're losing 18 for every peptide bond formed, and that's why it is 110. So if you have a 200 amino acid protein, then it will have a molecular weight of 220. 220 times 110, 200 times 110. All right, so, and the unit is called DA, which is Dalton. You won't hear that much in general chemistry, although it is there. Molecular weight unit is a Dalton, and it is frequently used for proteins to tell what size it is. So if you look at the structure of any of the amino acids in a protein, all the amino acids have lost their alpha amino group and carboxyl group because they are involved in the peptide bond formation. Except the first one, which has a free amino group, and the last one, which has a free carboxyl group. All other alpha amino and carboxyl groups are involved in the peptide bonds. Yes.
Can you just what's an alpha amino group and an alpha covalent? I know I asked that, but
Alpha is the way of counting numbers for carboxylic acid. So if you have a carboxylic acid, the next carbon is called alpha.
okay.
And the amino group is on that carbon, that's why these are called alpha amino acids. So all natural amino acids are alpha amino acids. And that's not true of not all natural, but all the natural amino acids in proteins are alpha amino acids. There may be some minor exceptions, but they are not in proteins. So all of these alpha carboxyl group and amino groups are involved in the peptide bond formation. So everything that we did about pK1, pK2, where is the PI, none of that is valid for a protein because those amino and carboxyl groups are not there. The only carboxyl group and amino groups there are from the side chain. So the total charge of a protein or the PI of a protein, the isoelectric point, those are not decided the same way that we did the calculations because the alpha amino and carboxyl group don't even exist in there. So the only thing that decides the PI are the side chains. And not just that, as I mentioned, the protein is not a linear structure like this, but it is a structure like this. And every amino acid influences another amino acid. So someone here can influence an amino acid here, and the PIs may be different. And the actual pKs are also different for the side chains, depending on the local environment. So if you have a sequence of a protein like this, you can feed it into the computer, and the computer can nowadays tell you what is the shape or what is the structure of the protein because it looks at which one is hydrophobic, how many carboxyl groups are there, how many extra amino groups are there, and with all that information it can actually give you a more or less structure of the protein. Alright, so we will stop here. I guess this class ends now, right?